Welcome to Module 6, which will walk us through Layer 2, also known as the data link layer, of the OSI model. The data link layer is important because it helps to move data onto and off of different types of physical media that are part of the physical layer. In this module, you will learn how the data link layer prepares data for the various types of media, compare how this is done between local area network and wide area network topologies, and how the data link frame is constructed and how it functions. What exactly does the data link layer do? In the OSI network model, Layer 1 is the physical layer, and just above that is Layer 2, the data link layer, as shown in the figure. The main job of the data link layer is to prepare network data from the upper layers for transmission across the physical network at the layer below it. The area of responsibility ranges from network interface card, or NIC, to network interface card communications of every device in the path end-to-end from sender to receiver. This includes allowing the upper layers to access the physical network media without the upper layers needing to have knowledge of what type of media is being used. Another function of the data link layer is accepting IP version 4 or IP version 6 packets from Layer 3, the network layer directly above, and encapsulating the packets inside Layer 2 frames. The data link layer also sends and receives Layer 2 frames while providing control over how they are transmitted and received, and performing error detection, and when necessary, rejecting corrupted frames. The data link layer also receives encapsulated data and directs it to the appropriate upper layer protocols. There is a lot going on at the data link layer. The figure here shows how the data link layer adds information to a packet handed off to it by Layer 3. When we talk about computer networks, a node is a common term used to refer to any device along a communications path that can receive, create, store, or forward data. Therefore, node is a broad term that refers to anything from an end device such as a laptop or smartphone to an intermediary device such as an Ethernet switch. If you think about all the different kinds of nodes there are, in addition to the different types of physical media that were discussed in Module 4, you can imagine what it would be like if the upper layer protocols like IP had to make provisions to connect to every different kind of underlying media it would encounter at every hop along the way from source to destination, or every kind of new technology being developed. In the figure at the data link layer, the network interface card, or NIC, on the PC adds Layer 2 Ethernet destination and source NIC information to a Layer 3 packet. The NIC will then convert this source and destination NIC information to a format that the physical layer underneath supports so that it can be transmitted across the network media. According to the IEEE 802 Local Area Network, Metropolitan Area Network, or LAN-MAN standards, which apply to Ethernet LANs, wireless LANs, or WLANs, wireless personal area networks, or WPANs, and other types of local and metropolitan area networks. The data link layer is further broken down into two sublayers, which are shown in the figure. The upper sublayer is called the IEEE 802.2 Logical Link Control, or LLC sublayer. The LLC sublayer's job is to communicate between the software at the upper layers and the device hardware at the lower layers. The LLC sublayer adds control information to the Layer 2 frame that shows which network layer protocol is being used. This is important because it allows both IP version 4 and IP version 6 to use the same NIC and network media at the same time. The lower sublayer controls the hardware and is called the Media Access Control, or MAC sublayer. Examples of IEEE standards at the MAC layer are 802.3, which applies to Ethernet network media, and 802.11, which applies to wireless network media. There's also 802.15, which applies to things like Bluetooth. Some of the functions of the MAC sublayer include controlling access to the wired or wireless network medium, providing source and destination layer 2 addressing, performing data encapsulation, including frame delimiting bits to synchronize between transmitting and receiving nodes, and detecting transmission errors. The MAC sublayer also provides something called media access control, which allows more than one device to communicate over a shared half-duplex medium. Full duplex communications don't require access control, but we'll get into that in a bit. As packets travel across a network from the source to the destination, they may and probably will cross different kinds of network environments, having different characteristics. For example, on an Ethernet local area network or LAN, usually there are often many hosts competing for access to the network media, while the MAC sublayer manages that contention. With serial WAN links, or wide area network links, on the other hand, the access method may just be two routers connected by a direct connection that doesn't require the services of the IEEE 802 MAC sublayer. Every router hop along the path performs layer 2 functions. The router accepts a layer 2 frame from whatever media type is used on the incoming interface, then de-encapsulates the frame to reveal the inner packet, re-encapsulates the packet into a new frame that is appropriate to whatever media is in use by the outgoing interface, and forwards the frame to the next hop in the path. To demonstrate using this animation, the router has two different types of network media, an Ethernet interface to the LAN and a serial interface to the WAN. Inside the router, data link layer services process frames. First receiving the frame from the Ethernet LAN medium, decapsulating it to reveal the layer 3 PDU or packet, re-encapsulating the PDU or packet into a new layer 2 frame suitable for the serial WAN medium, and placing the frame onto the serial medium, which is the next length of the network path. The Internet Engineering Task Force, or IETF, is responsible for the protocols and services within the TCP/IP protocol suite that occupies the upper layers of the network models and are documented using requests for comments, or RFCs. But unlike the protocols of the upper layers of the TCP/IP suite, a different set of engineering organizations define the open standards and protocols applicable to the TCP/IP model network access layer and the OSI model physical and data link layers. These organizations include the Institute of Electrical and Electronics Engineers, or IEEE, the International Telecommunication Union, or ITU, the International Organization for Standardization, or ISO, and the American National Standards Institute, or ANSI. This next topic explains how the data link layer works with different logical network topologies. Because the role of the data link layer is to prepare network data for being placed onto the physical network, the data link layer has to know the logical topology of a network so it can transfer frames between devices on the network. The topology of a network refers to the relationship and interconnections between devices on a network. There are two types of LAN and WAN network topologies. Physical topology describes the physical interconnections between end devices and intermediary devices. This may include device location details. Physical topologies are usually described as point-to-point or star topologies. Logical topology is more concerned with how frames are transferred from node to node. A logical topology would describe things like virtual connections and layer 3 IP network addresses. The data link layer uses knowledge of the logical topology of the network when deciding the type of network framing and media access control it will use to control data access to the network medium. This figure shows a sample physical topology for a small network. Each device is described in terms of its physical location. The next figure shows a logical topology for the same network. Although it looks similar, the information in the logical topology concerns network addressing and interface names. 3 common physical WAN topologies that wide area network or WAN devices typically use when interfacing with each other are point-to-point topologies, hub and spoke topologies, and mesh topologies. Shown here, the point-to-point physical WAN topology is the simplest and most common one, and is simply a permanent link between 2 endpoints. All frames on a point-to-point link can only travel between the 2 connected devices. The second common physical WAN topology is hub and spoke, which is a WAN version of a star topology. The hub or central site uses point-to-point links to interconnect the spokes or branch sites. The spokes cannot exchange data with each other unless they go through the central site. The third common physical WAN topology type is the mesh topology, which interconnects each node to every other node. Each link is a point-to-point link. The mesh topology provides high availability, but can be very expensive. Some networks may use a hybrid topology, meaning a variation or combination of topologies. An example of a hybrid topology is a partial mesh, which interconnects some but not all devices. In cases where physical point-to-point WAN topologies are using a serial communications protocol like point-to-point protocol or PPP, a node does not need to know whether an incoming frame is destined for it or not. The data link protocols can be very simple, in this case because a point-to-point link can only have 2 nodes, so all frames on the link can only travel to or from one of the 2 connected nodes. One node simply places frames on the media at one end, and the node at the other end of the point-to-point circuit removes the frame from the media. A point-to-point connection over Ethernet, on the other hand, requires the device to use the layer 2 frame header to determine if the incoming frame is destined for this node. In a point-to-point topology, the 2 nodes may be directly connected to each other or indirectly connected over a distance, crossing multiple intermediary devices. In this case, the intermediary physical devices in the network do not affect the logical topology, as shown in the figure. The additional intermediary physical connections may not change the logical topology, and the logical point-to-point connection will be the same. Turning from WAN to multi-access LAN topologies where end devices are interconnected using star or extended star topologies, as shown in the upper 2 figures. In a star topology, the end devices are connected to a central intermediary device, in this case an Ethernet switch, which even though not shown is represented by the point in the center. An extended star topology is simply an extension of the star topology, which interconnects multiple Ethernet switches, represented by the interconnected center points of the stars. Both the star and extended star topologies are easy to install, scale very well, meaning they're easy to add to, and are easy to troubleshoot. Before Ethernet switches were common, early topologies interconnected the end devices using hubs. Other legacy LAN topologies included an Ethernet bus topology, which is where end systems were daisy-chained and terminated on each end, and a legacy ring topology such as Fiber Distributed Data Interface or FDI and Token Ring, where end systems connected to each other forming a ring, which unlike the bus topology did not need to be terminated. In local area networks or LANs, duplex communication means the direction of data transmission between 2 devices. The 2 common duplex modes are half-duplex and full duplex. Half-duplex communication allows both devices to communicate on the shared media, but not at the same time. Only one device can transmit or receive at a time. Legacy bus topologies using Ethernet hubs use half-duplex, such as shown in the animation. Another more modern-day example of half-duplex communication would be wireless LANs or WLANs. Full duplex, on the other hand, means that both devices can transmit and receive at the same time on the shared media. This is demonstrated here. The Ethernet legacy hub has been replaced with an Ethernet switch, and both devices can send and receive at the same time in full duplex. By default, Ethernet switches operate in full duplex mode, but they can be configured to operate in half duplex if connecting to a legacy device such as an Ethernet hub. When configuring duplex, a host NIC and its connecting interface on an Ethernet switch must operate using the same duplex mode, or else there will be a duplex mismatch resulting in connection problems. The term multi-access network simply refers to any network having two or more end devices trying to access the network at the same time, such as Ethernet LANs and wireless LANs, for example. Sometimes multi-access networks have to have rules for how devices can share the media. Two access control methods for multi-access networks like LANs and WLANs are contention-based access and controlled access. Contention-based access is where half duplex nodes compete to use the medium, but only one device can transmit at a time. Contention-based access methods include Carrier Sense Multiple Access with Collision Detection, or CSMA-CD, which is used on legacy bus topology Ethernet LANs. Then there is Carrier Sense Multiple Access with Collision Avoidance, CSMA-CA, which is used on wireless LANs. The controlled access method is a legacy method where each node is given its own time to use the medium, which is inefficient because every device has to wait its turn to access the medium. Legacy token ring is an example of controlled access. Today's Ethernet networks operate in full duplex and therefore don't require either of these access methods. The half-duplex contention-based access networks, such as wireless LANs and legacy Ethernet hubs, require rules governing when a device can send and what happens when multiple devices try to send at the same time. The legacy Ethernet bus topology, which uses a hub, uses a set of rules called CSMA-CD, or Carrier Sense Multi-Access with Collision Detection. A collision is what happens if two devices transmit at the same time. With CSMA-CD, both devices detect the collision on the network. That is the collision detection, or CD, portion of CSMA-CD. Both device NICs compare data transmitted with data received, or detect that the signal amplitude on the media is higher than normal. The data sent by both devices will need to be resent in that case. To demonstrate CSMA-CD, in the figure, PCs 1, 2, and 3 are connected to a hub. PC 1 wants to send an Ethernet frame to PC 3. PC 1's NIC checks to see if any devices are transmitting on the medium. PC 1 does not detect a signal, assumes the network is available, and PC 1's NIC sends the Ethernet frame. The Ethernet hub, also known as a multi-port repeater because the hub regenerates all the bits it receives on one incoming port and repeats them out all of the other ports, receives the frame and sends it out to both PC2 and PC3. Again, it's a repeater, even though the frame is addressed only to PC3. While receiving the frame, if PC2 or PC3 want to transmit, they must wait until the channel is clear. As shown in the next figure, PC3 accepts and processes the frame because the frame's layer 2 destination address is for PC3, but PC2's NIC ignores the frame. IEEE 802.11 wireless LANs, or WLANs, also half-duplex in nature, use a different form of CSMA, which is Carrier Sense Multiple Access Collision Avoidance, or CSMA-CA. Like CSMA-CD, CSMA checks to see if the media is clear before transmitting, but unlike CSMA-CD, CSMA-CA doesn't detect collisions, rather attempts to avoid collisions altogether by waiting before transmitting. Each device on a wireless LAN transmits how much time it will need to transmit its message, and all the other wireless devices sharing the WLAN therefore know how long the medium will be unavailable. As shown in the figure, if wireless host A is receiving a frame from the access point, host B and C will also see the frame and know how long the medium will be unavailable. After wireless host A receives the 802.11 frame, host A will return an acknowledgement back to the sender, notifying the sender that the frame arrived. A contention-based half-duplex system like a WLAN does not scale well under heavy media use, which should be taken into account when designing wireless networks. Wired Ethernet LANs using switches rather than hubs are not contention-based systems when the switch and the host NIC both operate in full duplex mode. This last topic in Module 6 discusses the journey of a data link layer frame as it moves through a network. The structure of a data link layer frame will depend on the Layer 2 protocol in use, but a frame basically has three parts: a header, some data, and a trailer. When the network layer above hands a packet to the data link layer for transport, the data link layer prepares the encapsulated data for transport from the local NIC to the next NIC down the line by encapsulating the packet with a header and a trailer to create a frame. Encapsulating upper layer data inside a frame allows Layer 2 control information to be inserted in the header and trailer as values in different fields. This format gives the physical signals that will be placed onto the physical media a structure that is recognizable by other nodes and that can be decoded successfully at the destination. The figure shows generic frame fields that may or may not be used by all Layer 2 protocols. Data link layer protocols do add a trailer to the end of each frame, and that trailer is used to detect whether the frame arrived without errors. As part of the frame, the sending node creates a cyclic redundancy check or CRC value, which is inserted into the frame check sequence or FCS field to represent the contents of the frame. In the Ethernet trailer, the FCS tells the receiving node whether the frame experienced transmission errors. Device addresses at Layer 2, the data link layer, are known as physical addresses and are located in the frame header to specify the frame destination on the local network. The physical address is usually at the front of the frame so that the NIC can quickly look for its own Layer 2 address without having to look through the whole frame. Unlike Layer 3 logical IP addresses, physical addresses don't indicate what network the device is on. The physical address is a burned-in factory address unique to that device. That is why Layer 2 addresses are only used to connect devices within the same shared media locally. Let's walk through the journey of an IP packet as it travels from host to router, router to router, and finally router to host to review how at each point along the way the IP packet is encapsulated in a new data link frame containing the source physical address of the NIC sending the frame and the destination physical address of the NIC receiving the frame. Starting with the host to router portion of the journey, the source host, PC1, encapsulates the Layer 3 IP packet addressed to remote web server IP address 172.16.1.99 inside of a Layer 2 frame. In the Layer 2 frame header, PC1 adds its Layer 2 physical address as the source and the physical address for the adjacent interface on router R1 as the destination physical address. On the next leg of the journey, router R1 to router R2, R1 encapsulates the Layer 3 IP packet in a new Layer 2 frame, adds its Layer 2 address in the frame header as the source, and the Layer 2 address for R2's interface as the destination. On the last leg of the journey, router R2 encapsulates the Layer 3 IP packet in a new Layer 2 frame. R2 adds its Layer 2 interface address facing the web server into the frame header as the source physical address and the Layer 2 address for the NIC of the web server as the Layer 2 destination address. Although the frame has changed at every step along the way, the inner IP Layer 3 packet has remained the same from end to end. Beyond the local network, the data link layer address or physical MAC address is meaningless. That address is only used for local delivery. This is very different from Layer 3 addresses in the packet header, which are carried end-to-end from source to destination hosts, no matter how many network hops there are. In a TCP/IP network, the Layer 2 protocol operates in the NICs on computers as well as the interfaces on routers and Layer 2 switches. Protocols like the Ethernet protocols used by wired LANs and the IEEE 802.11 wireless LAN protocols are designed for multi-access LAN networks. WANs, on the other hand, use point-to-point, hub-spoke, and full mesh topologies, which call for different types of protocols, such as point-to-point protocol or PPP, high-level data link control, HDLC, frame relay, and asynchronous transfer mode or ATM. These Layer 2 protocols are now being replaced in the WAN by Ethernet. A LAN normally covers a small geographic area and uses a high bandwidth, cost-effective technology that can support many hosts. However, a high bandwidth technology usually isn't cost-effective for WANs that cover large geographic areas. In fact, the cost of the long-distance physical links and the technology required to carry signals over long distances usually means lower bandwidth capacity. The difference in bandwidth is usually what drives the use of different protocols for LANs and WANs. Layer 2 protocols commonly found in LANs are Ethernet and 802.11 wireless, while common data link Layer 2 protocols found in WANs are point-to-point protocol, high-level data link control, HDLC, and frame relay. This animation shows how the Layer 2 protocol can change at every hop along the path of a network from end to end. That brings us to the Module 6 quiz and wraps up our exploration of the data link layer.